so I will just recall some notation from yesterday. So my starting point today will be this art sphere dynamics. So I just rewrite this art sphere dynamics, which is really simple. So you have transport dxi over dt equal to vi, and dvi over dt equals 0 up to the time where, say, as long as xi minus xj is bigger than epsilon for all j, different from I. Okay, plus a specular reflection on the boundary. So that's the starting point, and what I would like to prove is that now if I look at this system, okay, and under some probability measure, which is this chaotic measure, initial measure, so a chaotic initial measure, which is, say, almost IID variables, which are this xi0, vi0. And now you look at the empirical measure. And I call pi epsilon of t, which is just 1 over n times the sum from I equal 1 to n of the direct mass at xi of t, vi of t. Okay, so yesterday what I told you is that, so essentially I did the computation. I did not so much computation, but I looked at the canonical setting, and today I will focus on the ground canonical setting. Okay, so in the ground canonical setting, you should just modify this a little bit, and this will be just 1 over mu. Okay, and I just remember that mu times epsilon to d minus 1 is equal to 1. Okay, so mu is the average number of particles. Now n is a random variable as well. Okay, so n is random. And once you have fixed n, you have this xi, vi, which are random variables with a distribution f naught. Okay, so up to the exclusion, these are independent and analytically distributed variables. Okay, and then you have this scaling law here, which is the Boltzmann grad scaling. Okay, so what you expect is that in the limit when epsilon goes to 0 and mu goes to infinity with this scaling condition, then this empirical measure should concentrate on the solution of the Boltzmann equation. Okay, that's the Landforce theorem. Okay, so now I will look at this ground canonical setting. Okay, so what I would like to explain is how you can look at this empirical measure. Okay, and so I will just start with a few definitions. So I will look at partition function and cumulants. So I just recall the ground canonical measure at time 0. So what I said is that you first choose n with this Poisson law. Okay, so this will be a small n. Here is the value of this n here. Okay, factorial n. Sorry. Then you, with this probability, you choose the n. And once you have choose the n, you choose the variables which are, say, distributed according to this f naught. Okay. Of course, you have to multiply by the fact that you have the exclusion. Okay. So dn here is just dn is just a subset of so the xi vi. Say td Rd to the n such that xi minus xj is bigger than epsilon for all I different from j. Okay, so you choose independent variables, you just modify this by the exclusion, then you here have a probability density provided that you renormalize everything by the partition function z epsilon. Okay, so that's my ground canonical measure. So both n and then xi vi, they are random variables. Okay, so now you see that this z epsilon is just the sum of mu to the n divided by factorial n times the integral of dn dn, and you sum from 0 to plus infinity. Okay, so that's the. Okay, so now what I will consider is actually a modified partition function, where essentially I will test this this integral against an exponential moment. Okay, so I will look at this z epsilon of h, or exponential of h, which will be the sum from 0 to infinity of mu to the n divided by factorial n. So this will not change. Then you have this initial data. And now I look at the expectation somehow of the exponential moment. So I will look at the exponential of h of z1 of t plus h of zn of t. Okay, so somehow this is just, say, up to the z epsilon here. This is just the expectation of this exponential, say, mu times pi epsilon of h at time t. Okay, so I'm just looking at an exponential moment. Okay, and you see that it's a bit different from what we looked at yesterday, because, say, if you look at the marginals, the marginals, they would be essentially the derivative of almost this guy, but where you do not multiply by mu here. So you see that this exponential moment is much bigger than the series that give you the. Yeah, so of course this is an analytic function with respect to h. Okay, and what I say is that in order to get the marginals that I defined yesterday, I should look at this series without the mu here. Okay, but here I try to look at this is to look at this exponential moment. Okay, and we will see that this is a very important quantity, and that from this quantity we can derive a lot of interesting quantity. Of course, the empirical measure, but also the variance, and this will be important for the measure concentration. But I will come back on this later on. Okay, so this will be the quantity that I'm interested in. So this, of course, depends on t here.
H is a function of which variables exactly?
Of zi. So zi is just the couple xi and vi.
But it has arguments that depend on n, then it's a function.
It's a function of one variable. Of a 2D variable. Yeah, and you have just the sum here. Yeah, so this is really the. So the first thing that I would like to remark is that if I say at time 0 at least, if I didn't have this exclusion here, you see that I would have a perfectly chaotic distribution. And then you see that this is also a product. Okay, and so this means that essentially here this is just everything is just a product. Okay, and so now if you look at the interesting quantity will be actually 1 over mu, the log of this quantity, Okay, so if you look at this quantity, in the case where everything, if the distribution is chaotic, completely chaotic, so a perfect tensor product, you see that the z epsilon, at least at time 0, of exponential of h is just a sum from 0 to infinity of nu to the n divided by factorial n. And then this is just a product. Okay, so this is just a product of the integral of f naught exponential of h dz to the n. Okay, so this is exactly the series expansion of the logarithm. And so if you look at this formula, this guy now, in the case where it's a product, okay, in the case of where the distribution is chaotic, then you see that essentially this guy will be just one term, which is this one. Okay, so this lambda, I think I will call it lambda of epsilon t. So in this case, lambda epsilon t h is just the integral of this. So in particular, you see that as a function of exponential h, you see that as a series, you have only one term. And this is just the expectation. Okay. Now the good thing with this, so this is the case where it's chaotic. But now is in the case where the distribution is not chaotic. What you expect is that you will still have a series expansion of this, which can be written 1 over factorial k, fk of exponential h minus 1. I think that's the way to the k. Okay, so that's a series with this argument here as a function of exponentially h minus 1. And this is the cumulative of order k. Okay, but you see that what is really important is that somehow, contrary to the marginals, the cumulants, they will not repeat the information. Okay, so in the second cumulant, you see that in particular in the Boltzmann grad limit, what you see is that the marginal, somehow they encode the same information because you expect that essentially the second marginal is just a tensor product of the first one. Okay, so essentially if you look at the moment without the mu here and without the logarithm, what you get is just an information which is repeated an infinite amount of times. Okay, while here if you look at this function now, you see that the first cumulant will be just the expectation. Okay, so you are very happy because this is what you would like to characterize here for the Boltzmann grad limit, so to get the Boltzmann equation. But then at the second order, you will not repeat this information about the average. You will have just an information about the variance. And at the third order, you will get still another information. So all the cumulants, they encode different information and they encode a different scale. Okay, so at each order, you have a different information. Which correspond to a different scale. So once again, I will come back on this later. But now you see that here, the reason why this is not a product. Okay, so of course there is this exclusion, the static exclusion at time 0. But then you see that there is another source of correlation, is that this z1 of t, okay, in general is not independent of z2, z3, and zn. Okay, just because you have this motion, and at some point, of course, if all the particles have just purely free transports, okay, all the particles would be independent, and so I would be able to make this factorization here. But in general, for time which are non-negative, you see that there is no reason that d1 does not depend on the other position and velocities. And so you see that you have a bit of correlations coming in the system and coming from the dynamics itself. Okay, so we will see that actually these dynamical correlations, they are much bigger. Say the order is much bigger than the correlation coming from the initial data. So essentially what I can do is just to focus on these dynamical correlations. Okay, so that's what I will do now, is to study the different correlations coming from the dynamics. Okay? So I will start with the notion of cluster path. Okay, so all what I will do today is really to try to study this functional lambda epsilon and its dependence with respect to time. Okay, so and we will also use this lambda epsilon next time to study the fluctuation. So essentially, what you have to remember is that, say, the first derivative of this lambda epsilon will tell you something about the average of the empirical measure, and that the other derivatives will tell you something about the fluctuations. Okay, so today I will focus on the first order derivative, but before looking at an equation for this first order derivative, I will try to have, say, uniform bounds on this series expansion. Okay, so that's really the goal today is really to try to understand this functional lambda epsilon. Okay, because then it will give you a lot of information. Okay, so as I told you, the first reason why it's not true. Okay, once again I just forget about the initial correlation coming from the non-exclusion, from the exclusion. Okay, and so now the reason why, the first reason why you cannot factorize the term here is that you have this dynamical correlation. Okay, due to the collisions. Okay, so we will first look at the correlations due to collisions. Okay, and then we will define a cluster path. So we will fix a time interval. Okay, so we fix a time interval 0t. And now what I will call a cluster path is just a set of particles which are all connected via collisions. Okay, so a cluster path is the trajectory actually of a set of particles which are all connected by collisions. Okay, so this corresponds to a graph, something like this. So you have some particles like this at time 0. Maybe these two will collide, and maybe this one then will collide with this one. Okay, and so these three particles. Okay, so this is a cluster path. Okay, so here you have a collision, and here you have a collision, and you have this particle. So that's time 0. So that's time. That's t, and that's 0.
You consider the connected cluster path?
Yeah, a cluster path, this is a trajectory of particles, so a set of particles which are all connected. Of course, you see that if I change the time interval, probably the cluster path will be different. For instance, if I look at this time interval, this will be in the same cluster path, and this will be in another one. Okay, so this is...
Right or on the left, there are other cluster paths.
Yeah.
You do not separately.
Separately, yeah, so something like this. So here, this is one cluster path, and this is another one. Maybe I should. Maybe, but at the moment, I fixed this time interval. Okay, so here you have two cluster paths, one in white and one in orange. Okay.
It's a way to So nice to know. Two collisions.
No, here you have just they are binary collisions. Yeah, because we no. I say what I said yesterday is that actually you can prove that if you start from this art sphere dynamics, you have multiple collisions, so 3 particles at the same, say, colliding at the same time. It's just for a set of measure 0. So you can just discard all this pathological situation. So you have something like this, and you see that, of course, if you look at this fixed time interval, you have a partition of the set of all particles in this cluster path. Okay, so then you get a partition. Okay, so for any initial data, you have a partition of particles in a set of connected sets. Okay, I don't know. Okay, I don't know. Cluster path is not really completely, because cluster path is a trajectory, and okay, this is not completely precise, but okay. Okay, so this means that I can go back to this definition there, and then introduce this partition. Okay, so what I say that for each initial data I can use a partition, and conversely I can just partition the set of all initial data in terms of how they will split in this cluster path. Okay, so this means that I have that z epsilon t of exponential h will be the sum from 0 to infinity of mu n factorial n. Okay, and then I will sum over the partition, say over k, and the sum of in partition in lambda 1, lambda k. So this is a partition like this of particles in cluster path. Okay, and then I have just something like the integral of f0 n, the indicator function here. The indicator function so lambda I should be a connected, so it should be a cluster path. Okay, so at lambda I is a cluster path. A product from I equal 1 to k. And also a product that, of course, 2 cluster paths, they should not interact. Okay, because then S is not a cluster path. If these 2 have a collision, then it's not the right partition. Okay, so I multiply this by the fact that I different from j. You have that lambda I should not collide with lambda j. And then it's a bit and then you still have the exponential of h of z1 plus h of zn and the dzn.
The partition strongly depends on t. You fix t first.
The capital T here, not the small t. No, the small t is
in between.
The small t is here, is just here. But of course, I will take small t between 0 and t. But a priori, there is no reason to do that. I can just say, I introduce this partition. Of course, it will be interesting to have the t between 0 and t. But
the partition is defined by capital T.
The partition depends only on capital T. Yeah. So if I write this, you can say, okay, but it seems like much more complicated than the previous formula. So why is it really interesting to do that? Okay, so you see that now, if by definition, if you have a cluster path like this, this means that the z, say, if z1 is in the cluster lambda 1, you see that actually the particle number 1 will see only the particles which are in the same cluster. Okay, so this means that this product here, I can just split it in parts which correspond to the cluster path, and then they will not talk to each other. Okay, so this means that I have also something like this. So I keep this lambda k, so this is a partition. And now I will try to have a product from I equal 1 to k. And then here I have that lambda I is a cluster. Then I take f0 to the length of lambda I. Okay, so it's a bit... and then the exponential of the sum of h for, say, j for j in lambda I. Okay, so this is really something which only depends on the cluster lambda I. Okay, and then of course you have the exclusion. Okay, but now if you look at just a cluster, so it just will not collide with any other particle, and so you can just consider this as a subsystem that just lives in a different space. So if you would like to compute this quantity here, so the integral of this, you see that just by exchangeability, you don't really care that it's particle number 1, particle number 2, or particle number 3. What is just important is the number of particles on their position. Okay, and so at this point, you can use the exchangeability to say that, so how can I construct this? I can just say that I will look at the sum over k. Okay, so I fix the number of clusters, and then I will just put the different particles in the different clusters. Okay, so this is just Fubini. Okay, so you look at the sum over k. The sum, now the only thing that that's really important are the lengths of the different lambda j. Okay, so the sum here. So now these are just clusters of a given size. Okay, so something like this. So maybe I should just say that these are the cardinal of the different clusters. So of course you have that mu to the n is just mu to the n1 plus n2 plus n3 blah blah blah. Okay, so you have the mu to the n I divided by ni. And then you see that the combinatorial factor and the product of the factorial ni divided by factorial n is just the different way you can arrange the particles in the different clusters. Okay, so this factorial ni, so n1 nk divided by n. Okay, and probably there is a factorial k somewhere. Okay, so there is also 1 over factorial k. Yeah. So of course this is not the right way. So this one, sorry. Okay, so this corresponds to the different ways you can put n1 variable in a packet, n2 variable in the packet, and nk particle in the packet, and then just by because you don't care that it's the first packet or the second packet, you have that. So this is really the combinatorics that tells you how you can put all the n particles, because you don't care of the label of the particles, in the different packets here. Okay, so now you have this something like this, and now you can put this mu to the ne divided by factorial ni with the, so now I have this product from I equal 1 to k of mu to the ni divided by factorial ni, and the, so this is ni actually, and the exponential of the h of, okay, I will just call it like this. And then I still have this exclusion. Okay, so this is just Fubini. So there are two things. The first thing is that I just forget about the labels of particles because of exchangeability. And so you see that choosing this partition is the same as taking all the particles and saying that you you put them into these k packets with cardinals n1 and k, and this is the factor which comes in this computation here. And then you just use Fubini and you get this. Okay. And so now if you look at this, and you forget that it's a complicated formula, you see that it looks like very much what you have above there, okay? Except that instead of looking at particles, you have now cluster paths. Okay, so you see that this guy is just the exclusion of the different cluster paths, so it's exactly plays the same role as the indicator function of the n. This guy is just something which is factorized. Okay, and then you have the same combinatorics, so the 1 over factorial k. Okay, so it's almost the same formula, except that you have replaced somehow the particles, okay, that you have. So for instance, in the static case, if you forget about dynamics, when you expand the exclusion of particles, the static exclusion of particles, you start with something which is really like this. So you have something which is a product, okay, maybe a complicated product, but still a product, times the exclusion here. Okay, and so now you see that you still have to do something because it's still not a product just because of the exclusion. So now the only thing that you have to do is to deal with this exclusion here. Okay, so is this first step clear for everybody? So I decide that, so I know somehow how to deal with the static case, essentially because people did that for quite a long time. So if you have a gas of particles and you have just the exclusion, then people know how to expand the exclusion, and that's what I will do next. But now it's more complicated because of this dynamical correlation. Essentially, the only dynamical correlations are the correlations which are due to collisions. Okay, and so I decide that, say, the elementary object that I will consider is not the particle, but the cluster path. And the cluster path is just a set of particles which are connected by collisions. Okay? And so just using Fubini, essentially, I say that now what I have is a gas, almost like a static gas, but a gas of cluster path. Okay? So that's, now we have a gas of cluster path. Okay, I think the formula, I hope everything is okay. I think so. Okay. Yes. Okay, I can put the sum here. Okay, maybe it's even easier if I put the sum over ni here. Maybe it's even... Okay, and all this I will call this measure nu of lambda I. Okay, that's... Yes?
Just to be sure I understand, so with this decomposition, you sort of set T fixed, capital T.
Yes.
You no longer view that as a dynamical problem. You
yes.
view this, as you said, as a static problem with different elementary objects.
Yeah. So what I say is, that, of course, what is important here is that the small t now is smaller than capital T, because the important assumption here, which is not an assumption, which is just a definition, is that on this time interval, so at time t, between 0 and small t, I should not have any interaction between the different cluster paths. Yes. Okay, so that's just a definition. But if I take any t smaller than capital T, then it's okay. Okay. Okay, so that's the first step, and now, of course, I have to understand this exclusion. Okay, so that's the next step.
If I take capital T large enough, I have only one cluster and no exclusion.
If you have, yes. So what you say is that probably I should take the T here. The T here is the same as the capital T.
Maybe not. Maybe the idea is
No, that's why. How many collisions will you allow at the end? A small number of collisions or further?
Yeah, essentially that will not be better than Lanford, so it's
1/5 on average.
Yes. So yeah, essentially all the particles will have 1 or 0 or 2 or a finite number of collisions. Yeah. But I agree that here the T now has to be the, else I would not have this this exclusion condition. Okay, so now I will expand the exclusion. Okay, so that's the next step. So that's what is called the cluster expansion of the exclusion. And so that's something which is very classical in even static thermodynamics. Okay. So what I have is the product for I different from j of this, the fact that lambda I should not interact with lambda j. Okay. So this is kind of mathematical artifact, this expansion, because of course that there is, so it's somehow from the physical point of view it doesn't really correspond to anything. But what we would like to say is that maybe it's a bit complicated to have an interaction, to force an interaction. So the fact that they do not interact is a small correction to just the fact that they are independent. Okay, so what I will write is that the fact that they do not interact, okay, is 1 minus the fact that they should touch each other. Okay, so that's of 1 minus the fact that, and so here it's really important to explain that it's really a mathematical definition. I will not change the dynamics at this point. I do not say that having no collision is 1 minus having a collision, but just 1 minus the fact that just the two things will touch each other, but without changing the dynamics, of course. Okay, so that's really important to understand that this expansion here is really a mathematical artifact. You see that in the maybe in the static case, it's easier. You say that, oh, I would like to compute the probability that I can put particles like this, and I say that they should not touch each other, and you will say, okay, that's the same as having 1 minus the fact that they overlap each other. But of course, this doesn't mean that in the real life they can overlap each other. Okay, so that's just a mathematical definition. Okay, so that's just a mathematical artifact, and that's what we will call an overlap. And the thing which is important with overlaps is that, of course, this means that you are at a distance which is less than epsilon, but still it will not change the dynamics. Okay, the dynamics is already encoded here. Now you will not touch the dynamics anymore. Yeah.
So here it's the generalization to clusters of the exclusion zone Dn, which you wrote at t equals 0, right?
Exactly. Yeah.
Okay. But then I'm not trying to understand this business mathematical artifact. I know that we had a discussion about that, but in the sense that initially it's not a mathematical artifact that particles don't touch each other, right?
Sure.
So here what changes? What's the difference here in this case?
No, actually, it's so the only thing that I want to say is that, say, and maybe it's, say, the negation of the fact that the clusters have no interaction. Yes. So the definition that they have no interaction is just the fact that they are at a distance which is bigger than epsilon. And so the negation of this is just that at some point the distance is less than epsilon, but this doesn't mean that this will change the dynamics. That's the only thing. Okay, so overlap means that at some point the two structures will be at a distance which is less than epsilon, but this will not say that when the particles are distance less than epsilon, then you should do a collision or something like this. Okay, that's just the fact that you can move these two structures here, and I will draw a picture. I can move this, and maybe they will overlap, but this will not change the dynamics. Okay, so the overlap does not change the dynamics. This is just a condition on the distance. Just a condition that there exists a time, tau 0t, such that, say, the distance between lambda I at time tau minus lambda j at time tau is less than epsilon. That's just the definition of an overlap. Okay, but then each cluster path does its own business. Okay. Okay, so typically what you would have is something like this. So now you have one cluster like this, one cluster, say, like this, and maybe another one that I will, maybe another one like this. So here you see that you have an overlap here, an overlap here, an overlap here. But this overlap, they will not change the dynamics. Okay? So these are overlap. And the other one, they are collisions. So this one, you have really a scattering and blah, blah, blah. Here, you just say that they cross each other without scattering. Okay, so maybe I should put something different for the collision on the overlaps. So collisions mean that you have a scattering. Overlap means that you are just crossing each other without any deflection. Okay, because this is just okay. This expansion. Okay, so now at this point we are exactly in the same situation as for the static exclusion, and I would like to expand this. And you see that there is one way to expand this, is to say that, okay, you just use the binomial formula or something like this, and what you get is that you will get the sum over all possible. So now you have all these k clusters. Okay, so you have lambda 1, lambda 2, lambda 3, and lambda k. Okay, and now you just expand this product here, and so you will get a sum over all possible graphs. So a graph. So for instance, I take this one. Okay, so I will have a sum over all possible graph with I don't remember gk graph with k. And now you see that if you have an edge in the graph, you take minus the indicator function that lambda I has to be close to lambda j. And if you have no edge, then you just take the 1. Okay, so that's the way you get that. So now you take for any edge in G, you take so I would call it ij, an edge in G. And you have minus 1 I, and probably it's the product. Okay, so that's just the expansion of the product. Nothing important here. Okay, but then I can once again plug this, and now where so I will do something which is very similar to here. I will decompose this graph in connected components. Okay, so that's exactly the equivalent of this partition here. Now I just look at a partition of my set of particles in connected components. My set of cluster paths in connected components. Okay, so we introduce the partition of the graph in connected components. So now you see that the equivalent to be in the same cluster path is to be in the same connected component of the graph. So this will be, and then the equivalent of the lambda 1, lambda k will be all these components, this connected component of the graph. Okay, so you can do exactly the same combinatorics here, the same Fumini formula, and then you get something which is essentially the final form that I will use. So you get that z epsilon t of exponential of h will be the sum from 0 to infinity of 1 over factorial, I will call it m. And then you have the product over, say, so the notation are just horrible, but okay. So I will have the integral of d nu of lambda 1, d nu of lambda ml, the phi epsilon of lambda 1, lambda ml, and to the power m. So I will explain where they come from, but so the d nu is this measure here. So this guy here is the nu. Okay, and now I'm just expanding this and this. Okay, so now here what I have is a partition in, say, m1 plus ml equal to k. So I have a partition in L components, or okay, maybe this should be L. Okay, and then M should not be okay. It's just horrible. Okay, I will try to. Yeah. Okay, I will just try to avoid this. Okay, so I have L is the number of connected components. And then M1 and ML are the size of each connected components. And this function here, I will rewrite it, but you see that it's supported on the fact that lambda 1, lambda m should be connected. Okay, so this phi epsilon, so it's supported on connected graphs. Okay, so this is exactly the same computation as here. Okay, so you do exactly the same Fumini, same combinatorics, and you get this. Okay, so the L is the number of connected components, and their size M1, ML are the size of each subgraph of the subgraphs. Okay, and then you have a formula for this phi, and I will keep it because I will need it. So this is a sum over all connected graphs of size m. Or I will give you the. So it's just the sum over all graphs which are connected of size m of the product for ij, the edge of g of -1 lambda I connected with lambda g. Okay, so the same formula. Of course, if m is equal to 1, it's just 1. Because essentially this set is just empty, and by definition, it's just anything to the power 0 is 1. Okay, Is it okay for everybody? So I just repeat. I start from the definition of this modified partition function. Then I have a first partition in this cluster path. So this is the point where I really use the dynamics to say, okay, some particles have collisions, and then I split in connected components. Okay. Then I simplify, or say I try to factorize as much as possible. This is really the point. You see that essentially what you would be very happy if everything was chaotic and you can factorize everything. So you try to factorize. The first obstacle to factorization is the presence of these collisions. And so you say, okay, now I just grouped particles according to collisions. And then I have something which is almost factorized. Okay? But then you see that having no collision is not exactly being independent. Okay? Just say that you have exclusion. And so you said, okay, but exclusion is almost independence if the exclusion is small. And so now you say that you like to say that exclusion is a small correction to 1. And so you look at this overlap and this aggregates, okay? And then you perform exactly the same. And now you have something which is, you see that you are really happy because now it's factorized. Okay, so if you take the logarithm of this, you see that you are really happy because you know that it's exactly the logarithm of this quantity here.
When you say you do the same, you start from the cluster path and then you...
Yeah.
So in each subgraph, you have both collisions and...
So the collisions, they are encoded in this measure nu here. So this nu tells you that you have a cluster path of size which can be anything between essentially 0 and infinity. The size of this guy is ni, so it's just given by this law here. Then you have a measure, so which take into account the initial distribution and also this test function h. Okay, so each of this packet now is in this small notation d nu of lambda I. Okay, and what I say is that then you have m packets like this, and a small correction to this, that these packets they should have some overlaps. Okay, so if you draw a picture of something like this, this is like this. So here you see that m would be equal L would be equal to 3, okay, because you have 3 big packets, and inside each packet you can have 1, 2, or say any number of collisions, but these are really packets in the sense that all particles in the packet, they are connected by collisions. Okay, so this really corresponds to this structure here, that you have essentially now 2 reasons why you can be in the same connected component. Either you are connected by collision or you are connected by overlap. Okay, and then you see that you have, so either you first look at the dynamical packets with the collisions, and then you look at the overlaps, or you can also say, now I have a lot of correlation. There are either collision or overlaps, and I can describe them at the same time. Okay. And so we will see that in the Boltzmann equation, somehow this collision, they are responsible for the essentially for the gain term, and the other one for the loss term. So, but actually you will deal with all this collision and overlap at the same time.
So the C are responsible for the gain term in...
It's not completely true, but I will explain after.
Okay, and just also so that I understand, if you could raise the upper board. Yeah. So wait, so here you're summing over G. Use the set of, because I can't read it here.
So here I sum over. So what I say is that when I expand this product here, I get all the graphs.
Oh, you summon all the graphs?
All the graphs. So GK is, this is the set of all the graphs. And now, once I have a graph, for any graph, I can decompose this graph into its connected components.
And over there?
Over there, in CK, so these graphs, they are connected. Okay, so CM, so maybe I should say that GK is the set of all graphs with K points, okay? And CK is the set of all connected graphs.
So it's a number of nodes or vertices or whatever, right? K.
All connected graphs with K nodes. Okay, so that's really what you are doing here is exactly the same as looking at this partition, but you do the same for the partition in graphs, in connected graphs. Okay, so that's, yes?
Do I understand well if you, in a sense, what you are doing is like looking for cluster graphs, but in a smooth epsilonized version of it?
Smooth. Maybe can you repeat the question?
I say it's like, is it like the same point of view, but just you say they are in the same stuff, not only if they collide, but if they are close at epsilon?
Not really. What I say is that, so in this second part, what I say is that here you see that I have these two guys, and I say they have no collision. Okay, but having no collision, so or at the static level, being having no overlap is not the same as being independent. Okay, because being independent means that you have no condition at all, while having no collision means that the distance of the particles in the two graphs, in the two trajectories here, they should stay at distance epsilon for any time. If you have no interaction, if in the dynamical system you have no collision, then it means that the distance has to be greater than epsilon for all times. And this is not the same as being independent. Okay? So overlap is just the negation, so it's here. Overlap means that there exists a time such that the distance will be less than epsilon.
But how it cannot be a collision? So
just because there is no dynamics at this point. I just try to figure out what it means to be the contrary of being at a distance bigger than epsilon for all times between 0 and t. And so the negation of the opposite of being at a distance greater than epsilon for all time is just that there exists a time such that the distance is less than epsilon.
So this overlap is basically a mathematical trick.
Exactly. It's completely mathematical. So this doesn't correspond to physics. So really, maybe I should draw these pictures one again. So when I say I have a first ball here, and now I would like to choose a second ball with the exclusion condition, I cannot choose this particle under the Lebesgue measure because it cannot overlap with this one. And what I will say is that, okay, choosing this particle is almost like choosing with the Lebesgue measure, so it will be 1 minus something that is forbidden from the physical point of view, which is this. But you see that this condition is not a physical situation, it's forbidden. So what I say is that being admissible is 1 minus being forbidden. Okay, so this is overlap is a situation which is forbidden from the physical point of view.
But maybe, I don't know if this would perhaps not make things simpler, but you could have defined this overlap just by a condition on the sort of maximal or minimal distance between the paths in your clusters, and that would be perfectly.
So that's the minimal distance. So.
Yeah, but I mean, in this way, well, even I mean, like some norm, like you did for t equals 0. Yeah,
exactly. But the only thing that I want to say is that overlap is a situation which does not occur from the physical point of view. Yes. It's really this situation here. And what I say is being admissible is 1 minus this. And this, of course, will not happen. But there is no dynamics at all. It's, dynamics is already encoded here. I know that.
In the usual, I forgot how it's called, expansion of the potential in the Boltzmann formula, there is this formula which computes the correction from the potential, no? I forgot how it's called.
Oh, you mean the, what's the...
Minus V, then you expand really in V, which means the region where there's some interaction.
Yeah.
Okay, it has a...
But I think, yeah, it's more or less the same. This is really a cluster expansion. Oh, maybe, yeah, then it's different. I think it's maybe time to stop for 5 minutes. 5 minutes. Okay. Let me just write one thing about this function here, and then I will stop. Okay. So something that is important with this function phi here, and it will be really useful in the. So it's well-known results in combinatorics, very classical because of course this. So it's really important here that you have the -1 side, that this is really an indicator function, okay? But so you see that being a connected graph, you have still a lot of choices to have connected graphs, okay? And so essentially, if you just forget about the sign here, this sum here would be very big, okay? But now if you look at the size of this guy, because of the -1 here, you have some cancellations. Okay, and then I will go back on this cancellation trick later on to identify the Boltzmann equation, but this is something which is well known for this exclusion thing. And then what you can prove is that the size of this phi epsilon, so essentially what you have is that it's smaller than the sum. Now you don't take all the graphs which are connected, but all the trees. So meaning that they are minimal graphs. So they have only m-1 edges. And then you have this ij in the edge of t. Okay, so this means that somehow you will count. So you have cancellation between the different graphs. Okay, so for instance, maybe I can just draw a picture with 3. Okay, so I have a set of 3 that should be connected. So I will try not to forget any of them. So no, they should have the same here. So maybe it's not the right. Okay, maybe 3 is not enough, so maybe I will not draw a picture because it will be complicated. But essentially, it tells you that you have you can identify for each, say, you have a mapping from the set of all connected graphs to trees. Okay, so there is a kind of mechanism to identify a minimal graph once you have a graph. Okay, and then you can prove that essentially all the other edges, sometimes they have a 1, sometimes they have a -1, and so they will cancel each other. Okay, and so in the end, what you obtain is that this guy, so the sum is essentially of the order of the sum over the tree, so of the order of factorial k.
So, c'est un peu, ok, c'est un peu de l'autre côté, on a quelque chose. C'est une bonne idée de phi epsilon. C'est de l'autre côté aussi, on a quelque chose.
De l'autre côté, de quoi?
Donc là, tu as juste une majoration. Est-ce que tu as une minoration?
Je ne sais pas. Non, je ne sais pas. Je pense que oui.
Maybe another question. Keep asking stupid questions. So here, this is, if I understand, you're bounding a phi, which is itself a sum, right?
Yeah.
You're bounding phi by a sum over a smaller set.
Exactly.
Okay.
And that's the point. Here, if you just forget about the signs, then you get a big set because the number of possible graphs, connected graphs, is at least factorial k to the square, I think. But then you can see that for each graph here, you can identify a structure which is a minimal graph, and then see that all the other edges. So for all then you look at all the graphs which have the same image by this mapping. Okay, and then you look at all the other edges, and sometimes you have, sometimes you don't have, but they cancel each other because once you have 1 and the other time you have -1.
And the inequality here is really with a 1, with some constant, or? It's
the indicator function. So essentially here you say that say something which is in all the graph which have this t as a minimal graph. Okay, so of course all these they have always the edge in t. Okay, so this is supported on the graph, okay, which have at least all the edges in t. Okay, but then you see that all the other edges they will compensate. But I will come back on this argument later on to identify the Boltzmann equation. Actually, it's something which is a bit more complicated because you have more complicated graph, but it's exactly the same as here. So you prove that essentially you have some cancellation, and that in the end you get the equation which is much simpler than what you would expect.
So here this exclusion thing is like only comes from the initial time, right? Because you have
no the exclusion here.
No, I mean, it's not something that you do at initial time, but like you have to do this because at initial time they are not fully independent.
No, this is because I really define this cluster path as being connected components, and so this means that if these are connected components, then this other cluster path has to be at a distance at least. So it's really a dynamical exclusion. It's different from the static exclusion at time 0. It's really the fact that you cannot superpose these trajectories. Really, the picture is really this one. This situation is forbidden because the orange one should not overlap the other one. Okay, so this is the same principle, but the exclusion now is not just the exclusion at time 0, but really the exclusion of the whole trajectories. Okay, I think we should have a small break now, and yeah. Okay, so now we have this expression here for the modified partition function. Okay, so it's we are really happy because now it's essentially factorized, and so what I have to do is to prove that. So now if I take the logarithm, of course I get this thing here. And what I have to do is to prove that this quantity is uniformly bounded, okay, for all epsilon. Okay, then if I have a series which is uniformly convergent, then I will be able to play with the series, remove some terms which are not so big, and so on. Okay, but the first thing I have to do is to say that I have uniform bounds for this series. Okay. So here I have to say that I will just give the heuristic argument and how you can prove things, but okay, I will just avoid some technical difficulties which are not very interesting, but of course takes a little bit of time and energy to deal with them. Okay, so so once again, the only thing that I have to look at is this part here. Okay, so if I look the lambda epsilon t of exponential h is just I think it's just so probably there is product which is missing here. No, yeah, this is a product sum here. Okay, so this is the sum over m over something which is just a tensor product of d nu to the n and phi m. Okay, so if you would like to control this, and maybe there is a 1 over factorial m at some point, which is probably missing. Okay, so let me check. Yes, there is a 1 over factorial m here. Yeah, this would be complicated. Okay, so the first thing I will try to do is to show you how you control one d nu like this, and then I will try to explain how you can say group this small packets with this connected graph. Okay, so now let's look at the nu here. Okay, so you see that at first sight it's not so nice because you have this mu to the n, but just recall that mu is very, very large. It's like epsilon to the minus d minus 1. Okay, so mu is a really, really large number. So you see that this guy seems to be really, really large. But now you see that what is, so now f naught, say it will be a bounded function, so it's something like constant to the n. This guy, this h is a nice function, so it's also a constant to the n, so you don't care. And now, of course, you have this. So now the question is how small, say, what kind of smallness this indicator function will give you. Of course, it's an indicator function, so as a function, as an LMTD bound, you have nothing better than 1, okay? But say, now if you look at the L1 norm, we will see that this guy is very nice, and essentially it will compensate not the mu to the n, but mu to the n minus 1. Okay? So, recall what is so now we have this indicator function that lambda is a cluster path. So what it means that you have a picture like this with some collisions and maybe something like this. Oh no, it's okay. Let's look at this, and maybe I should have at least one recollision. Okay, so okay, like this. Okay, so this is a nice cluster path. You see that all particles are connected by collisions. Okay, and so now what I would like to say is that each time I have a collision, of course, this imposes a very strong constraint on the position because you see that, for instance, these two particles, they have to be, so their initial position have to be in a cylinder such that at some point you will touch each other. Okay, so if these are particles 1 and 2, you see that at type 0, you have that x1 minus x2 minus, say, v1 minus v2 times tau for some tau which is less than t. This has to be epsilon omega. Okay, so this means that this tells you that this x1 minus x2 has to be in a small cylinder, which is of size, so x1 minus x2 is in a cylinder, the size of which is something like epsilon to the d minus 1 times, say, v1 minus v2 times t, say capital T. Okay? So that's very good because you see that this epsilon to d minus 1 exactly compensates 1 mu. Okay, so each time you have a collision, you would like to say, oh, but then each time I have a collision, I will gain one mu. Okay? Of course, you cannot do that, say, as many times as you want. And for instance, if you have a graph, so if you look at the graph of this collision, and this graph has a lot of edges, so everybody will collide everybody a lot of times, then you will not, you do not expect that you will gain a factor 1 over mu each time. Okay? So the way you have to proceed to gain, say, the optimal smallness is to say, okay, now I will look at, and you see that it will be a bit like this procedure here to extract a tree. So here you also have to extract a tree. So you start from time 0, you say, oh, here I have a collision. So I keep this edge between particle 1 and 2. Okay, so I have particle 1, particle 2, I keep one edge here. Okay, then I have a second collision here between particles, say, 1 and 3. Okay, so this collision, they are okay because you have no loop in the graph. Okay, then you look at this collision here, and this collision here is between particle number 2 and particle number 4. So you still have a graph here, which is minimal because you don't have any loop. Okay, And then here you have another collision, which is between particle 3 and particle 4. But here you see that it's not good, because then it's complicated. You have an additional condition, and now it's very complicated to know that you are in the intersection of so many tubes. Okay, so this one you don't like it, so I just put a dash line here, and I will forget about this collision. Okay, that doesn't mean that this collision doesn't hold, but I just mean that I will not try to use some information coming from this collision. Okay, and now you have this collision between particle number 1 and the particle number 5. Okay, and so now, the first step is to identify a tree, a minimal. So a tree is a minimal connected graph, such that all these collisions somehow they are independent. Okay, independent means that you have enough degrees of freedom to write independent condition. Okay, so first step, identify, say, a tree, and this will correspond to what is called clustering collisions. So each time you add a new particle in, say, you have a new cluster in the graph. And you see that for collisions, it's really important that you proceed with this order. So you start at time 0 here, and you really proceed this way. Okay. So you look at the first collision, and the second collision, and the third collision. Okay. So now you see that you can write the condition for this x1 minus x2 to be in a cylinder. Okay. But then you see that when you will add the particle number 3, okay, the particle number 1 and 2, they will do their own stuff here. But now you will add here the particle number 3, but you see that you still have all degrees of freedom on this particle number 3, because you have no condition at all at the moment on the particle number 3. Okay, so you first write the condition that you should have a collision here. This will give you, say, a condition, so you fix particle number 1, okay? Then I say, oh, but now I have a condition that particle number 2 has to be like this or like that. So I have now a condition. So I will integrate over x2, and this will tell me that x2 has to be in a small cylinder. Okay. Now I have this the new position, and I say, oh, but now I will add the condition that x3 has to be in a cylinder. Okay. And then I will add the condition that x4 has to be in a cylinder. Okay, and so you see that you are identifying that way, say, independent constraints. Not really independent, but say constraints that you can deal with iteratively. Okay, so this really corresponds to independent constraints. Okay, so this means that if you perform then the integration in the right order, so first of all, you will, then you have to think. So you say that first of all, you will integrate over the x5 to be in the right cylinder, and then so you have then to integrate in the opposite order. Okay, but this is just Fubini, and so you each time you will gain this factor epsilon to d minus 1 times the time, and the time they are ordered. Okay, so this means that what I gain as a smallness, so just by integration, I gain epsilon to d minus 1. So I will cheat because I will forget about this velocity because this is technical and I don't want to do that. And then I have this t, but you see that the t, they are ordered. So when I will integrate somehow, I will integrate over a simplex. So what I get is this t to the I don't remember, it's n. So this is n minus 1, and this is n minus 1 divided by factor n minus 1. Factor something like this. Okay, so I do that. So you see that if I identify a tree, okay, in a set with n particles, I have n minus 1 edges. Okay, so I have n minus 1 constraints. And when I integrate, you see that I get t to the n divided by factorial n. Okay? Now, of course, this is once I have chosen one such tree. Okay? And you see that now I have to say that I can have any tree. I have to sum over all possible trees and all possible ordered trees. Okay, because now I know that first of all, so the way I do that is that this is the first collision, then the second collision is this one, then the third one is this one, and the fourth one is this one. Okay, so now I have to sum over all possible trees with a time order. Okay, and so how many trees you have is something like factorial n, so this is for the number of trees, and then another factorial n for the order. And this is for the number of trees. Okay, but now you see also that in the definition here, you have 1 over factorial n. Okay, so now you have to multiply this by 1 over factorial n and by the mu to the n. Okay, so if you gather everything together, you see that you have mu to the n. That's okay. It will not compensate exactly this one, so you have it's just one mu which is remaining at the n, and then okay, so there is a c t to the n. Okay, so you see that you are very happy with this because, of course, if the time is short enough, and that's where you get this Lanford's restriction. You see that here you have a geometric series which will be convergent. Okay. And so in the end, you get only something which is of the order of mu. Okay? So once again, here, this is, so the second step is to use the independent geometric constraints, and then you have to add everything. But here, once again, I'm cheating because you see that I completely forgot this V1 minus V2, and that's why you need to use, say, exponential weight and to compensate, and you need to use some symmetry arguments because, okay, so this is now very technical, so I don't want to go further in this direction, but essentially step 3 is to resum everything. Okay, so after this, you see that what is important is that you have the size of this guy. And now let me just tell you something about the and here you see that it will be really important to be either in the Wool space or in the torus. Okay, so you see that when I have performed all this, I said that I can fix the position of particle number 1 the way I want. Okay, I have no restriction. The first condition tells you that 2 has to be like this or like that. So then I just play with the relative position of the particles. And you see that it's really important that everything is translation invariant. Okay, so here the norm is not really an L1 norm. You see that you still have a bit of search because you can still translate the whole thing. And of course, it will not change the size. Okay, so if I decide to take the same cluster here and move everything in X, of course, it will be the same size. Okay, so these are the two things that you have to remember now. So the size is like this, and you have some translation invariance. So you have still 1 degree of freedom. Degree of freedom in X. So for instance, you can take, I don't know, the center of gravity of whatever you want, but okay, so you can fix one position, the position of one particle that we would call root particle, but once this root particle is fixed, then you have this L1 bound for the other integration parameters. Okay, so it's somehow it's an L-infinity bound in X1 with L1 and L1 with respect to all other parameters. Okay, so I still have 1 degree of freedom, and it will be very important for the next step. Okay, so is this first part okay? Yes?
And the C is of order what?
The C, so the C, you see, it depends on the norm of F naught. It depends on the L-infinity norm of exponential of H. And actually, it also depends on this decay with respect to velocity, because you see that essentially each time you get something like a power of V here. So it will also depend on the decay. Okay, so typically it depends on L-infinity norm of F naught, L-infinity norm of exponential H, and the decay to the power N. That's okay. bit too fast, but yeah. At least it depends only on F0 and H. And of course, constant that depends on I don't know, the volume of the ball and this kind of things. Okay, so that's the way you can control this d nu here. Okay, but now it's not the end of the game because now I also have to control the phi m. Okay, and so now for the phi m, essentially I will do exactly the same. So I will use this this thing here, and what it tells you is that you can control the phi m by the sum over all possible tree. So you see that you are exactly back to the fact that you have a tree, and then that you have this overlap condition each time you have an edge in the tree. Okay, so then you do exactly the same. Okay, so you say that you have 1 over m, factorial m, the phi m, and you have, of course, the d nu m, but the d nu m, what it tells you is that you have a factorial mu to the m. This guy comes from the d nu m, the L1 norm. Okay. So you have something like this, which is very, very close to the definition of nu. Okay. And so now you see that this guy, it's smaller than the sum over Tm, a T in Tm, of this, the edge of T of lambda I close to lambda j. But what it means to have lambda I close to lambda j means that you should change the distance between the two trees. So now you remember that for each tree you still have 1 degree of freedom. Okay, so you have your two trees, they are rigidly defined by the dynamics, and now you play with the trees and you just change their relative position. Okay, and you see that in order that the distance is smaller than epsilon, then you did that the two trees essentially the relative position, they are in a small cylinder of size epsilon to the d minus 1. Okay, so now I will explain why I'm so the stem step. So here there is the tree is already identified. So now I will just so I have n minus 1 conditions. So n minus 1 geometric conditions. Which tells you that essentially you have that relative position of the two trees, the two clusters, is in a cylinder of size epsilon d minus 1. Then there is something like a bound on the velocity and a bound on the time. Okay, so now it's not completely true because for the first one, for the clusters, you see that you really look at the distance between two particles. Now you look at the distance between a cluster with say n1 particle and the other one with n2 particles. Okay, so here normally it's not this, but you have something like n1 and n2, where this n1 is the size of the first cluster, and n2 is the size of the second cluster. Okay, so it means that it's not completely true. I can first sum over all the n for each cluster, and then I will deal with the overlap conditions. So you see that I should first do that and then sum over m, but it will not change anything. Okay, so essentially what is important is that you will have this epsilon to d minus 1, and you have n minus 1 condition like this, and so in the end what you get So now you have the trees, they are not ordered, but you don't have order on the overlapping times. So essentially you get exactly the same thing in the end. So you get that step 2. So there's actually to be combined with the other part, but you get another CT to the, so I think it was m minus 1, mu to the m divided by factorial m times t to the m, sorry, ct to the m times epsilon d minus 1 to the m minus 1. And then I have factorial m, which is the number of trees. Okay, now you see that there is no order on the times, but of course you have less trees if you have no order on the tree, so it's exactly the same. Okay, so here I do not tell you how to deal with this n1 and n2, but it's exactly the same as for the v1 and v2 here, so you need a bit of symmetries, and you need to be careful, more careful when dealing with all the sums. But you see that in the end, when you sum everything, what you get is that this lambda epsilon is just of the order of mu, okay, and that's it. Everything is. So the right, I don't remember exactly what I gave you as the definition of lambda epsilon, but you see that you have to renormalize by 1 over mu in order that you get something which is uniformly bounded. Okay, so what is a good quantity is 1 over mu, the logarithm of the expectation of the exponential moment. Okay. So normally, I don't remember exactly what I give as a definition, but normally it's 1 over mu here because it's 1 over mu, the log of the expectation of the exponential moment. Okay, that should be the right definition. I don't remember whether I put this 1 over mu at the very beginning or not. Okay, so that's the way you get uniform bounds on, and so I have, okay, very little time to do everything else. So I will see what I do. So maybe I will just look at the at the low density limit, say general things about the low density limit, and next time I will try to identify the Boltzmann equation because I cannot do everything now. Okay. Okay, so now what we know, okay, is that we have a uniform bound, and actually everything is not just a uniform bound, but everything is uniformly convergent as a series in exponential of h. Okay, so that's much better. You have analytic properties. Okay, so this quantity 1 over mu, the log of the expectation. Of course, the expectation depends on the measure, which. Okay, so this is lambda epsilon t exponential h. So this guy is uniformly convergent. As a series h. So the first thing that I would like to say is that just with this, without computing any limit of anything, you already get a measure concentration property. Okay, so the first thing is that and so that's related to what I said at the very beginning. Okay, so maybe I could write this as mu pi epsilon of h t. Okay. And the way you can do that is to say replace the h here by a constant, say s times h, okay? And now you look at the derivative of this with respect to h, with respect to s at s equals 0. Okay, so I can look at this function. Okay, so it's a very nice function. And now if you look at the derivative respect to s, okay, so I look at the derivative at s equals 0. So you see that when you differentiate, then you get that you will have the empirical measure here, which come here. Okay, and then you take s equals 0, so this guy is just 1. And so in the end, what you get is just the expectation of the empirical measure. Okay, so when you differentiate this guy and then take the derivative at time 0, then you get the expectation. Okay, so this gives you the expectation of pi epsilon t. Okay, and now if you take the second derivative at s equals 0, so I will not perform this, it's not very funny, but then you get exactly the variance. And this is exactly what I told you at the very beginning, that if you look at this function as a series, so which is, this function is usually called the cumulant generating function. Okay, so the name of this is a cumulant generating function. So if everything is factorized, then you get this and then 0 for all the other cumulants. But if it's not factorized, then the first term is still the average and the second term is the variance. Expectation of pi epsilon t minus the expectation of pi epsilon t to the square. And maybe there is a normalization, I don't know. Maybe there is a 1/2 or, no, I think it's something like this. So this is actually 1 over mu epsilon times the, so if you compute the second derivative, you get this. Okay, so this means that the second derivative actually is bounded because you have a function which is analytic on with a radius of convergence that somehow you control, which is okay, which is not 0. And so this guy is bounded, and you see that this tells you that the variance is like 1 over mu epsilon. Okay, so this tells you that you have concentration. It doesn't tell you what would be the limit, but at least you know that you have concentration. Okay, so concentration is just for free once you have the bound. Okay, so concentration of the measure comes for free. For free. It's not completely free because there is a bit of work before, but okay, so you don't need to look at the limit of this guy to say something about the fact that the measure will concentrate. This just comes from the fact that you have a bound, and this gives you the concentration directly. And actually, it will give you much more because, of course, you control the second derivative, but you also control the third derivative, the fourth derivative, and so on. And so it will tell you much more. It will give you, information about large deviation. So this one, you see that it's exactly the order of the central limit theorem. So this is something that we will discuss next time. So it tells you that the fluctuation of the empirical measure around its average is of the order of 1 over square root of mu epsilon, which is exactly the order of the central limit theorem. But so of course you don't control only the first two cumulants, but all cumulants here, and so it will also give you something about large deviation. Okay, so that's just a first thing. Now, of course, you would like to say something about the limit of this guy, because everything will concentrate, but you would like to say what is the limiting, the asymptotic behavior of this.
But the concentration here essentially comes from the fact that you had assumed initially IID, and you did not lose, the collisions did not mess up the independence of things.
It mess up a bit, but not say, yeah. So maybe what I should say is that if you look at the initial time, say this error here is not it's not like epsilon to the d minus 1 over 2, but epsilon to the d over 2. Okay, so the size of the fluctuation at the initial time, they are much less than the dynamical fluctuation. Okay, so if so what I say is that the static fluctuation, so the initial fluctuations, they are of the order of epsilon to the d divided by 2, while the dynamical fluctuation they are of the order of epsilon to d minus 1 divided by 2. So that's much bigger. So that's why here I didn't pay much attention to, because there are also some correlations coming from the initial data that I didn't really deal with, but anyway, they are much smaller than the dynamical fluctuations. Okay, but yes, I agree that at least at time 0, essentially what you have is that it's almost factorized. If you, in particular, if you look at this scaling here, you see that you don't see any fluctuation at time 0, because this guy in the limit, this guy will be just 0. Okay, so with this scaling at time 0, there is no fluctuation at all. Okay. Okay, so I still have a bit of time, and I would like to discuss how you get the limiting functional. So that's the second point here for the limit. And I think that's the important point here. So you see that we have a very nice representation of this cumulant generating function, with where you see that, say, essentially the term of if you summarize here and you look at this as a function of h, you see that if you look at the power n, so the cumulant of order n, this means that you have n copy of h, okay? But then you see that it will be n copy that are connected either by collisions or by overlaps. Okay, so that's the first thing. So the cumulant of order n, it corresponds exactly to a set of n particles connected by overlaps or collisions. Okay, so the contribution to this series as a series in exponential of h, so the term of order n is exactly correspond to a graph like this. Okay, so you have some collisions, and then another graph with okay, something like this. There's an overlap here. Okay, so that's typically the contribution, any contribution to the cumulant of order n. Okay. Now, what is different between the lambda epsilon and the limit is that in the limit you will have just graphs like this, which are minimal. Okay, and what you have to do is first to prove that if at some point you have either cluster paths with recollisions like this. Okay, so we saw that this guy is somehow an additional constraint. Okay, so this one is the one, the dashed one. So what we call a recollision, so something that is not really used to get the smallness. But of course, if you add it, it adds some additional smallness. Okay, so each time that in a graph like this, you have a recollision, then the contribution of this guy will be small. Okay, so what I say is that it's not true that I will gain an additional epsilon to d minus 1, but you will gain something like a power of epsilon. Okay, so if at some point you have a non-minimal graph, then the d nu, which correspond to all these minimal graph, they will be much smaller. Yeah.
Just about the terminology, maybe you already say that, but what is a minimal graph?
A minimal graph is a tree.
Okay.
So yeah. Except that here you see that if I consider first the collisions and then the overlaps, then it has to say it's a tree of trees, but still it's a tree. Okay, so it means that I have n minus 1 connection and that's it. Okay. Okay, so what I say is that the contribution of all graphs which are not minimal, so if you have at least one loop, okay, then you can prove that the contribution is negligible in the limit. Okay, so that's really say the important part of the proof is that if there is a recollision or non-clustering overlap, so just maybe I can draw a picture. So a recollision will be something like okay, maybe it's easier to have a non-clustering overlap. I can just do like this. Okay, so I have two overlaps between this graph, these clusters and this cluster. So I have one additional one. Then you can prove that, of course, once this Y structure is completely fixed, having this orange line which cross both this one and this one, it's an additional constraint, and this costs something. So from the geometrical point of view, it's not completely obvious to control this kind of recollisions or non-clustering overlap. Okay, but here the non-clustering overlap is this one. Okay, so non-clustering overlap is this, and recollision is this. Okay, so if you have at least one of these, then you can prove that it will not contribute to the limit. So the contribution is negligible in the limit. And so this means that in the end, what you have is that all so all elementary cluster paths are just connected by a tree, and then you have also a tree for the overlaps. Okay, so exactly n-1 connections, no more. Okay, and this is really important, and I will tell you why. So here you have exactly, so in the limit, the cumulant of order n correspond to having exactly n-1 overlaps or collision. So maybe this oh, okay, I should stop now. Okay, so maybe just I just said that okay, so the lambda here. So you would like to get the asymptotic formula for this. So I said that you have exactly you have only connection by trees here, only connection by a tree here, and the other thing is that of course the measure will become singular. Okay, so instead of having collision or overlaps at a distance epsilon, there will be a collision or overlap which are exactly pointwise. Okay, so this means that the other thing that you have to change here is the singular measure but this probably I will explain once more next time. So you have all this, but you see that, say for fixed epsilon, this corresponds to the fact that the particles will collide at a distance epsilon or will overlap, but at a distance epsilon. Okay. Now in the limit, of course, epsilon is 0. Okay, so this means that now they will exactly cross each other. So now the measure in the limit will be singular, and maybe I can just do it for one collision, and then I will stop. So for one collision, you see that the condition to be in a cylinder, blah, blah, blah. Okay, so what you have is that what you would like to have is really this mu times epsilon to the d minus 1. Okay, so what I say that mu times mu times the fact that x1 minus x2 is in a cylinder, such that you will have a collision, blah, blah, blah. This will converge to a singular measure, which is a Dirac in x1 minus x2. Okay, and then you have this v1 minus v2 dot omega plus. Okay, and you have the d omega, dt, and dv2. Okay, so here I assume that that x1 is fixed, and now I would like to have x2 in the cylinder, which corresponds to a collision with x1. And this I said that in the limit, of course, you have to rescale by mu, else the indicator function to be in a very small cylinder, it will just converge to 0. But now if you multiply by mu, you see that it corresponds essentially to the size of the cylinder. And so this will converge to a Dirac mass in x. And then you have a reparametrization of x2, which is given by this d omega dt. Okay? So that's what is important. So if you know that you have this, and that you have only the minimal graphs, then you get exactly the limit for this function here. Okay, so you can prove it iteratively just by looking collision after collision and overlap after overlap. And if you have the right order that I used before to identify the clustering collisions, then you can just use this iteratively. Okay, so after that, you get the limiting functional here. And next time I will try to explain how you can deduce from this both the Boltzmann equation, which is the law of large numbers, and also the central limit theorem and large deviation. Okay, so at the end of this lecture, what we know is that we have a uniform convergence for this series, and we know what the limit of this Cumulon generating function is. Okay, and so next time we will start from this limiting Cumulon generating function, and we will get say all this characterization of the limit.
So pi of t concentrates on a solution, the solution of Boltzmann equation.
Yeah, it will concentrate.
Starts with f0 at time 0.
Yeah, exactly. But so at this moment, I have not yet identified the Boltzmann equation.
Yes, but it concentrates on something.
Yes. And this something is, I know that this something actually is the first derivative of the limiting functional here. Because if I have uniform convergence of the series to another series, then you have also the convergence of the first derivative to the first derivative. Okay, because this is really in an analytic setting. So if I can just characterize the derivative of the limiting functional, then I will get the equation satisfied by the limit. And that's what I will do next time.
Très bien.
I think there is a question.
Non, mais attends, on va faire les questions après.
OK.
On remercie d'abord. OK, maintenant, dans l'ordre qu'il faut, maintenant on peut poser les questions.
So, Yeah, so with this cluster expansion or whatever, you told us you use already some cancellations, right?
Yes.
In the sums, right? Yes. But also, if I remember, you also said at the end, you will derive the Boltzmann equation on roughly the same time interval as Lanford, and Lanford, if I remember, was not using any kind of cancellation. So Lanford just puts absolute value inside the collision interval, right?
Yeah, so the difference here is that, so in Lanford you somehow keep only part of the information, which is, so you start from a particle and you just look at the history back in the backward direction. While here you see, you keep the history of the whole packet for the whole time. Okay? And so the cancellation that I will show you is just to remove the parts which, so for instance, if I have this, if I have in a packet and I have something like this, okay, and the particle that I'm interested in is this one. Yes. What I say is that I will be interested in this, but this I don't care. Okay. And so essentially what I will do is to go from this representation with real clusters, because they are just related by real collisions, to something which looks like the representation of which is used in Lanford. So I will the cancellation that I will use are just to remove this part here.
Okay. And you mean by doing that, it's not enough to increase the time on which you derive the Boltzmann equation?
No. If you would like to go further, and that's what Deng, Annie, and Ma do, actually you have to split the time in small time slices. And
yeah, because you want to be able to repeat after. Yeah, okay.
Because you see that here, say, there is no way you can really expect these clusters to be, say, if you have even a stochastic dynamics where you just add edges, so this is exactly what happens here with a probability which is proportional to time. Mm-hmm. Okay. Then you see that you have a macroscopic component after a finite time, which is essentially this Lanford time, or maybe twice, or maybe so something which is related. So the fact that you have a macroscopic component on this time is not that we don't compute the thing without care. It's just because if you really look at the cluster, the size of the cluster, you will have an infinite cluster after a finite time. But of course, you keep far too much information when you keep all this. You could imagine to remove all this. This is not really important.
But in your proof, you benefit from the structure of the initial data. Now, yes. If you want to cut into smaller intervals and repeat the argument, then when you start,
it's not like this. Yeah. You don't repeat the argument. You keep, say, you keep the way you do that is essentially that you will put all the slices together, and each time you will remove some bad guys. Okay. But say for the guys, if you would like to arrive to time t, then you have to connect everything to time 0. It's not like that's what I said. I don't know if it was yesterday or the day before, but it's not. You cannot derive the Boltzmann equation as a partial differential equation in the sense that it's local in time. It's really the only thing that you can do, actually, that people can do up to now, is really to derive the mild form of the Boltzmann equation, so really related to the issue. So yeah, you can remove things which are bad for any reason at some point. So you can remove some bad things, but still you have to connect time t to time 0.
No, I agree with that. Yeah, but then it means that if you want to cut a time interval, I mean, however large it can be, if you want to cut it into smaller pieces, then your starting point in the piece after time 0, I mean, maybe the second piece, will have an initial data which will be much, much worse than the one that you have in your argument here, right?
Yeah.
Because here you choose the...
But you have no information about the measure at this time.
Yeah.
I think that's really important that, you see that, say, on the one hand, all this land force proof, you need really a very precise knowledge of the measure at time 0. Yeah. Okay, so you need to know that essentially it's completely chaotic up to this very small fluctuation. Okay, but now you see that in this there is no proof where you can say that the measure at time t, which is bigger than 0, is like this or like that. You don't know. Yeah. The only thing that you know is that the projection of this measure on a finite space essentially has good properties. So that's why this is not really an iteration. Actually, we don't know how it's very bad. Actually, the measure itself is very bad.
And is the sense of time important in your proof? If I change t minus t, are you proving
the
Boltzmann equation?
Yeah. So you just change the sign of that. So it will relax towards equilibrium when t goes to minus infinity. It's exactly, yeah. You just change the velocity in minus the velocity and then you get the same Boltzmann equation. So really the idea is that you just lose information going forward or going backward is the same. So you have perfect information on your initial data, so at time 0, but then going backward or forward is the same.
No, but it's the reverse here. You have perfect chaos at t equals 0 and you have correlations up and down.
Yeah.
That's the reverse of what Boltzmann had in mind.
Yeah, that's why I said, that's what I said, that say, from the physical point of view, this proof is not really
There is a problem for the future.
No, what I said is that it's a mathematical justification, but from the physical point of view, it's not satisfactory at all, because here you said collisions, they will destroy chaos, while of course, what we expect is that collision, they should help to get chaos. Yeah.
Again, the word chaos means gas.
So essentially, the problem is still completely open.
Laure.